We started off with a brute force implementation where we iterated over every number in the range. Then we moved to an optimized solution where we only iterated on the numbers that we needed to add to the sum. The requirement we have been satisfying so far is we don't only have the sum but also the actual multiples whose sum we have as the answer. If we look closely at the question, it did not ask us about the multiples, it just needed the sum. If we consider that, we can move on to a much more optimized solution. In this optimization, we get around 27.38% improvement. We can get up to 99% improvement in finding the sum if we let maths do all the work. Yes, if we let maths do all the work, we don't even need iteration. So there's a concept in mathematics called arithmetic progression, and we know formulas that allow us to calculate the sum without knowing the actual elements in the progression. Let's move to the sketchbook for a quick reminder of the formula. Let's define what an arithmetic progression is. An arithmetic progression has an initial number, say 1, and then we keep adding a specific distance called d. Suppose for this the distance is 3, then we'll have 4, 7, 10, and so on. Now the formula of sum of first n terms of this arithmetic progression, which we mark as s of n, is known to be n by 2 a plus l. For our use case, we have to find this. We do not know this. We know this. We know this. And there is another formula that we know from arithmetic progression, is that the last number is equals to a plus n minus 1 of d. And as we see, we know this d to be 3 or 5 or 15. We'll get to the correction later. We know L, we know A. So it's simple to associate n in terms of L, A and D. We'll get n equals to L minus A by D plus 1. If we substitute this over here, we'll get S of n equals to L minus A by D plus 1 divided by 2 into A plus L. Now as we can see, we know all of the elements in this formula. So let's call L as the stop value, A as the start value, and D as the step. This is the stop value, this is the start value, this is the step, this is once again the start value, the stop value. We know all of these, and you can simply put this equation in and find the sum. Now that we have an empty canvas, we can summarize S as stop minus start by step plus 1 divided by 2 into stop plus start. Now do we want to simplify this a bit? Let's do that. So this will be stop minus start plus step, stop plus start divided by 2 step. And this is simple enough to be coded into our solution. Let's move forward with this. Switching back to code, we'll close all the open files. So we'll close others and then close this one. Come back to 3NN optimized. This top is the largest number below this max number that is a multiple of 3. So the strategy is find an AP sum with the range 3, find an AP sum with the range 5, add them both and apply correction for all of the multiples of 15, which is the AP sum of the range 15. Let's first find the stop value. Let's define this function. The stop value itself will be an integer. Let's call this calculate stop. It will calculate the highest number below the max number, that is a multiple of step. We'll take in int step and we'll take in int max number, and let's return say max number. And we don't want the max number to be included in the stops. For example, if it's 1 to 10 and we're dividing by 5, we don't want 10 to be included, so let's do a -1 over here. Now dart allows for a special operator, int division. So we int divide by 3 for removing any remainder and multiply by 3. This should be our answer. The only difference is instead of 3 it will be step and step. This will give us the highest number below the max number, that is a multiple of step. Let's calculate the sum of AP. It will also be an integer. Let's call it sum of AP. This will take 3 parameters: the step, stop and start. Int start, int stop, int step. This will return a function. So there's one factor, stop minus start plus step, other factors stop plus start, and then 2 into step. So stop minus start plus step, stop minus start, multiplication, division by 2 into step. Let's put it in brackets. As we can see, we know from the formula and from mathematics that this value will always be an integer. But since there's a division in here, the compiler, the programming language, the computer would tell us that this is a type of double. To make sure that we get an integer, we can call any of these functions either round, ceil or floor. So we'll just do a floor. Now we can start looking into modifying the sum of multiples less than function and just see how cool this can get. We're doing sum of AP. Start is 3, stop is calculate stop, step is 3, max number is max number, and step is 3, plus sum of AP. Start is 5, stop is calculate stop, step is 5, max number is max number, step is 5 again. Do a minus, again a sum of AP, this time 15, stop is calculate stop, step is still 15, max number is max number, and step is 15. Close this up. This will auto format. We no longer need iterables. Switching to multiples of 3 and 5 test.dart. Run this and some tests failed. The expected is 23, but we're actually getting 9, which means there's something wrong with our implementation. Let us try to figure this out. When we write these arrow functions and we want to do a console log to understand what is happening and whether this is returning the right value or not, we'll need to do a command dot. We'll need to convert to block body, and then we'll need to assign it to a variable, then print that variable and stuff. It's kind of hectic. I don't prefer doing things that way. I just found out slightly better way of doing things. We have this printer of type T on main.dart. We can simply cut this from here, make a new file in helpers, printer extension .dart, paste it here and import. Now we can switch to this optimization file. We're importing helpers / printer extension and doing a print object. Reformat the code and just run test.dart and we will see 950. Let's understand what these are. 9 is the lowest multiple of 3 below 10. 5 is the lowest multiple of 5 below 10. 0 is the lowest multiple of 15 below 10. This means that our calculate stop function is working just fine. Now we'll do a dot dot print object after sum of AP and run the tests. Scrolling on the debug console, we see that there is 995000. At this point, it is hard to figure out which console log is coming from which print object. And there is a slightly better solution for this. Instead of print object, we are going to make a new file. Let's call it runner extension dot dot. No camel case. We are doing snake case all the way. Yeah. And let's copy this class printer and modify it. We want a template string and we want to print that. So instead of print object or printer, we'll first rename it to runner and we'll call it run on object, and this will take a function that takes a type of t and we'll call it f. We're doing a f this or on whatever object is being called on. Let's see this in action. We are going back to optimized dot dot. We're going to replace this printer extension with runner extension. We will remove print object and use run on object. We'll remove print object and use run on object. This will allow us to pass another lambda function which will take a result, and we can do a print over here and pass a template string max integer below max number, that is a multiple of step is result, and just do a format document. And as we can see, this is a simple way of logging wherever you want. We'll repeat this with sum of AP. So we are doing run on object and we're getting a result. We're doing a print call, now specifying a template for the print call. It would be something like this: sum of AP bracket start comma stop comma step is result. We'll format the document again and we will run test. Now we have a much better log. Now let's see. Sum of AP of 3 9 3 is 9, which is wrong, because if we take 393, it's 3 plus 6 plus 9, it should return 18. So we can say that something is wrong with this formula. So this is stop minus start plus step, stop minus start plus step, stop plus start, and two step. So stop minus start plus step, stop plus start. So we could figure this out. Now if we run this, we'll see that all of the tests have passed. Our optimization works. Let's see what is the gain in performance. If we go to main.dart, we don't have to make any changes. We just need to run this again. And we will see that a gain in performance is around 95.55%, which is significantly greater than the 27 or so percent that we were getting. Since we're logging a lot to the console, it also is taking a significant amount of processing. We just comment these two lines out and we get our pristine function over here without the logging. This is how I have really been in love with leveraging extension functions. Code looks much cleaner. We don't even need this import. So I'll comment this out. Let's run main again. We're getting 99.69% improvement. It's always above 99%. The exact improvement is always above 99%. We used the concept of arithmetic progressions, allowed maths to do most of the work. We are no longer iterating, and this gave us a huge increment in our performance gain, way above from 32 point something percent or 27% to always being above 99%. Thanks a lot to Rohit and Sumit for pointing this out. This definitely has been fun on how some mathematical work can save the computer a ton of performance, and this is a super optimized version of this problem. And I know I promised that I'd give you the brute force version of the second question today, but since we see it's a collaborative thing and you have come up with a much better solution than I did, it was hard not to make a video like this as opposed to moving forward. It's to learn more and more and have a sense of growth. We have explored a lot in this video. We have seen how we can use this 5-line extension function to super improve our logging experience, make our code look much cleaner, use arrow functions through and through. We also saw how instead of just writing function f, we can write a better signature to make the code more robust. And we also saw how by using maths we can get a 99% gain in the algorithm performance. That's it for today. Stay tuned for the brute force version of question 2 of Project Euler in Dart tomorrow.